Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we're going to have another look at Brian Mullin, a structural engineer who put out a series of flat Earth videos a couple of years ago. Now, some people have asked why I'm bothering with him. This is still an influence on the flat Earth. These wrong ideas are still misleading them. So it needs to be addressed. That's number one. Number two is Mr. Mullin's just vanished. I don't know if his employers talked to him or what, but he just vanished. He never put out any sort of a retraction. He never corrected any of his errors. He just left the videos out there and went on his way. So they still need to be addressed, and that's why I've decided to address them. Now today we have another video from Brian, and that is the rotation of the atmosphere. So let's cue up the music and see what he has to say.
Spinning, rotating, I really think it's the same thing. So anyway, Earth is rotating, right? And so let's say we're going to freeze the Earth at that moment. Freeze the Earth with the atmosphere around it, assuming that the atmosphere is rotating with the Earth. And that's what I have drawn on the board here. Okay? So here's the Earth down here. All right? And let's say that this line right here is the equator. When you're looking down on it, the equator is right here. Okay, so we're just going to say this line is the equator, and then this is the edge of the atmosphere up here, and then there's space out here. Now this is obviously not the scale, this is just conceptual. Okay, and so at the equator, the circumference of the Earth is roughly 25,000 miles. And so to figure out the instantaneous velocity of the Earth as it spins around its axis on the equator, you divide the circumference by the time it takes to make one revolution, which is 24 hours. And when you do that, you get roughly 1,038 miles per hour. Okay? And so we assume right here that this is the Earth rotating at 1,038 miles per hour. And I said in the video, and people have said in the comments, that you can just say that that's zero. Okay? And so what I want to do is look at this atmosphere and look at 3 points and 3 elevations, okay? A, B, and C. We know that it's all moving with the Earth and not getting left behind, right? That's the assumption. And so we will say at this moment we expect all of these points of air to make one complete revolution and come back to the same spot in 24 hours, right? Because the atmosphere moves with the Earth. The atmosphere never gets left behind. So right off the bat, since we know the velocity is equal to distance divided by time, we can say that VA, the velocity of point A, is greater than the velocity of point B, which is greater than the velocity of point C. Because point A has a longer distance to travel in 24 hours than point B, and point B has a longer distance than C, because the circumference of their path is greater, right? So I've got A up here at the edge of the atmosphere, space up here, B right here around 6 miles where planes fly, and C near the surface of the Earth.
All right, let's go ahead and reproduce Brian's diagram, but we'll label it with a little bit more information that's kind of essential to understand this problem. So this is a cross-section of the Earth at the equator, through the equator. So we're at the north and we're looking down at the Earth. The Earth itself is rotating from west to east in that direction. Now we have 3 heights that he talked about. One was at the surface, one's at 6 miles, and then one that he had labeled as the edge of space. But we're going to actually put a number on it, 62 miles. Now another thing that we have to look at is what is the radius of the Earth at these different levels? Well, at the surface, it's 3959. At 6 miles, it's 3965. And at 62 miles, it's 4,021 miles. Now, if you calculate twice that times pi divided by 24, you'll get the circumference divided by 24 hours, and that'll give you the linear speed at that level. So at the surface, it's 1,037.5 miles. At 6 miles, it's 1,038 miles. And at 62 miles, it's 1,052.7 miles. Now, Brian labeled these rotational velocities, but as we'll see in a minute, he's got a crucial disconnect that he's made. This one he called VA. That would be the velocity of rotation at the edge of space with a radius of 4,021 miles. Okay? He labeled this one VB, and that would be the rotational speed at 6 miles with a radius of 3965. And then this one he labeled VC, and that would be the surface rotation at 1,037.5 miles an hour. Now, just to kind of put a few things in perspective, the difference between this and that, actually the difference is 15.5. What Brian stated very clearly was that VA is greater than VB, which is greater than VC. Okay, now that is correct in all fairness to Brian if you're using these numbers here, because these numbers are based on the radius of the Earth at that height. However, that has absolutely nothing to do with the speed of the air at that elevation. Now, in reality, what's going to happen is this. The exact opposite of what he thinks is going on. Now, let me go ahead and explain why that happens that way. There's this thing called the conservation of momentum. So if we look at the air in this packet right here at the surface, how fast is it moving with the rotation of the Earth? 1,037.5 miles an hour. Now, when it gets up to 6 miles, it needs to be going forward an additional half mile an hour. What force exactly is going to push it forward? Well, there is none. Now, Brian identifies this, but doesn't make the connection. I'm going to make the connection for him. So, the air right here is going at 1,037.5 miles an hour. When it gets up here, an hour later, it's still going 1,037.5 miles an hour. So where's that packet of air going to be? Is it going to be in the box? No. It's going to be there, half a mile behind the box. And likewise, if we took a packet of air and moved it up to 62 miles in the short space of 1 hour, just for consistency, where would it be? It would be here. So that's half a mile. And this one on top, it would be 15.5 miles. That's the way it goes. Brian is working on the understanding that the air is in lockstep with rotation like the spokes on a wagon wheel. The problem is the rotational speed here at the hub is slower than the rotational speed out here at the rim. Unless there is some sort of a force acting on this to push it forward, that's not going to happen. It's going to lag behind. I'm going to use a different color for that because it's that important. The air is actually going to do this. Now, as that goes around the Earth, there'll be a lot of little curved lines like that, where the surface of the Earth is dragging the air above it with it as it rotates. Now, we're going to come back to this a little bit later. So at 6 miles, the air is moving half a mile an hour slower than the rotational speed at that altitude. What's that going to feel like? It's going to be a 0.5 mile an hour wind going that way. So if you looked at a column of smoke going up, it would be as if there was a gentle wind pushing the top of it half a mile an hour by the time it got up to 6 miles. That's what a column of smoke would look like on a clear day, by the way. Up here, that's a 15.5 mile an hour wind. And what little air is up there? Not really much. You wouldn't even notice that. But in between, it's a variation between 0.5 and 15.5. It's nothing. If you were flying from the west to the east, it would be between a 0.5 and maybe a 15.5 mile an hour headwind. That's all it would represent.
There's no friction between space and the atmosphere, right? Because there's nothing in space. So an object in motion stays in motion unless acted upon by an outside force, right? But that's kind of strange when you think about that air at higher elevations has to be moving faster to keep up with the ground below it. Because air moves up and down, right? Hot air rises, as we know, and cool air sinks, right? So how does the air speed up? When it's heated, it rises, but then it has to start moving faster. Now, even if it's only a little bit faster, the difference in these velocities, if you calculate them, isn't much, but they do have to be greater, or they will start to get left behind. So, how that is explained, I don't know. I haven't really found anything to talk about how the air has to be moving faster.
Now, Brian brings up an excellent point here. If the Earth was rotating and the atmosphere was going with it but had its own circulation within it, would there be an effect noted? Well, of course there would. Cyclones, trade winds, even the cells in the atmosphere. Now, the cells that are in the atmosphere, if this is the North Pole up here and that's the equator, there's a group that circulate that way. There's a group that circulate down here over the tropics, and there's a group that circulates in the temperate areas. This is how our weather works, and that has to do with the rotation of the Earth and the dynamics of the atmosphere above it. So go ahead and carry on, Brian.
There's things flying around in the air, different pressures, all kinds of stuff is happening internally as it all moves with the atmosphere. Now, I would think that eventually something's going to have to give it a nudge to keep it moving with the Earth, so to say. The energy would be lost, okay? But not to mention that, there are things that enter our atmosphere. There's meteors, all kinds of stuff is constantly is supposed to be entering the atmosphere from outer space. So that is pushing back on the atmosphere and wanting to slow it down. And so the common explanation for how the atmosphere keeps up with the surface of the Earth is by friction between the air at the surface. Let me use a red marker for this. There's friction here pushing back on this cubic foot of air down here that's at the surface. And then that's transferred through internal friction, internal shear forces within the fluid, because air is essentially a fluid, okay? It has viscosity. And so these internal shear forces are transferred all the way up throughout the layers of air, right? Just the air pushing against itself, the friction carries that force all the way up to keep the atmosphere moving with the Earth, right? Well, the problem I have with the thing that doesn't make sense to me, and this is why a lot of this is why I ignored it in the first episode, though I didn't explain it, is when you create friction, you create heat. You rub our hands together. It's actually kind of cool here today. Rub my hands together to warm them up. That creates heat. Heat is essentially kinetic energy. And so when something creates heat on the Earth, or when the Earth is heated by the sun, where does that heat go? Well, if you watch Balls Out Physics episode 4.1, I talked about how the accepted explanation for how things don't just get hotter and hotter and hotter is that it radiates out into space, right? So heat from the Earth radiates out into space, into infinite space, and that's lost forever. So this process right here, this friction process, the shear force process, creates heat, and that heat is escaping. Therefore, this whole system would be losing energy, wouldn't it? We say that heat is really kinetic energy, and kinetic energy is equal to 1/2 mass times velocity squared, right? And so this kinetic energy, I assume, is going down. The kinetic energy of the atmosphere is going down because it's losing heat. And since I hope we're not losing mass to infinite space, losing our air, that leaves only velocity to go down. So not only does the speed of the air relative to the surface of the Earth have to increase as you go up in elevation, because the path it has to travel, the length of the path, the circumference, increases. We also have this problem with losing energy. I don't understand how this could work.
Oh, Brian, you are just so close. You're red hot, but you're just not getting it, are you? Let me help you out. Now, first of all, your first error was thinking that the atmosphere goes straight up like a spoke on a wheel, and by necessity would have to have some sort of a force to make it go faster as it got closer to the rim of the atmosphere. That was an error on your part. There is no force doing that, and the atmosphere does indeed lag behind. Second, your frictional forces. Now, this is a little grain of truth that you have. For example, if we have an incline and I put a weight on it, and that incline is covered with Teflon, there's not very much friction. That weight will go down a long ways, and not much heat will be generated, but some will. However, if it was covered with sandpaper and I put a heavy weight on it that had a rough surface, it would slide down a little bit, but friction would rapidly bring it to a halt, and a lot of heat would be generated. You know, I don't want to confuse anybody. Over here, I kind of referred to Brian's thoughts as the rotational speed at a particular level. But then he started, when he came up with this expression, he was talking about the speed of the air. So I'm talking about the speed of the air here as well. Now, if you looked at the speed of the air in a frictionless environment, the surface speed of the air would be 1,037.5 miles an hour. As it went up to 6 miles, it would lag behind the spot on the Earth where it was generated, because it's going slower than the rotation would be at that level. Same thing at the edge of the space. But the speed that they would all be doing would be exactly the same 1,037.5 miles an hour. However, as Brian correctly points out, we don't generally have a packet of air go from the surface to the edge of space. What happens is that packet of air affects the packet above it, which affects the packet above it, and so on and so forth. What happens is the packet on the bottom exerts some frictional force on the one above it, which drags it along. But some of that frictional force is lost as heat, as Brian correctly pointed out. And what happens when you lose some as heat from that friction, your velocity goes down slightly. So in reality, the surface speed will be the fastest, followed by 6 miles, followed by 62. And that loss of speed will be due to the heat generated by friction reducing it. Now, this is mostly a theoretical concern because the atmosphere is much more dynamic than this. We're just looking at one particular variable, and that's the friction of the surface due to rotation on the atmosphere above it.
This increase in velocity that you have to keep up with the Earth doesn't make sense, and then the heat loss to me. Another thing a lot of people have said is you can set the velocity of the Earth equal to 0, right? Because of relativity, we just say that the Earth isn't moving for the plane problem, right? So if we say VC is 0, then VB and VA both have to be greater than 0 to keep up with the Earth, or they'll get left behind in 24 hours. So how does it all work? How do these things blow and move all over the place but still keep up with an Earth that's rotating? How does that work?
Well, Brian, since you asked, let me go ahead and help you out here. The reason you can't understand how this will work is because your thought process behind how it is working is incorrect. You think that the atmosphere acts like a spoke on a wheel. It doesn't. It lags behind in the upper atmospheres. Your entire presentation was trying to make it appear as though it was a spoke on a wheel. Now, why didn't you figure this out, Brian? What is Newton's first law of motion? In order for this air to catch up with that wagon spoke, a force will have to act on it in that direction. There is no force acting on it in that direction. Therefore, by definition, it cannot be a spoke. Now, why do I have to tell a structural engineer this very basic fact? This is something that I would get upset if my son got wrong in the 8th grade. Now that said, we're going to go on to a two-part episode next. The first part is going to be dedicated to his misunderstandings of Newton. The second part will be Cavendish. So I hope that you'll join us. I think it's going to be a very interesting episode. So this is Bob the Science Guy signing out from Northern Michigan. Thank you so much for stopping by. We'll see you again soon.